Howdy, everybody. Here for day 11. So far, I've had a lot of fun. Hopefully, you are all having fun doing it too. I just love to solve puzzles. Uh, I also sometimes speak English well. Uh, so let's just get on with it and talk about the day. Um, the problem is called Plutonian pebbles, and uh, this actually goes back. Is a similar one to one that we've done in the past a few years ago. But so the way you solve it may seem familiar. But the gist is you find a whole bunch of these stones that are in a line and they have numbers on them, and uh, you notice that every time you like blink your eyes, the numbers change, and things change with these line of stones. And there's some rules that apply. You notice that there's these rules that apply every time you blink. Um, and so if a stone is a 0, it becomes a 1. If it has an even number of digits, it gets split into 2. So it gives you an example here. If the number is 1,000, the left number becomes 10 and the right number becomes 0. So it splits. And then if neither of those two are the case, you just multiply the number by 2024. It notably says the order is preserved, which is potentially important, um, depending on how you go about solving it. However, it's kind of funny because at the bottom, what it just asks you is how many stones there will be after blinking 25 times. So in that case, while it says the order is important, it's not clear to me why it's actually important. So I find it interesting that it's in bold. It's possible that I missed something. So if there's a reason why the order being preserved is important, maybe you can show it to me, because it didn't seem like that was the case. But the way to think about this problem is you're going to have a list of numbers, and for each of the numbers, for every iteration or every blink, you're going to apply these 3 rules. And it's really just these 3 rules. So imagine you have a small array. It actually shows you a good example here, right? You have this array right here. Are these 2 values, these 2 stones? You blink once, and what happens? The 125, it doesn't apply to the first 2 rules. So you multiply it by 2024. 17 does have an even, so you split it, right? And then then the next blink, you can see that 253,000 gets split into 253 and 0. The 1 gets multiplied by 2024, and the 7 gets multiplied by 2024. And you basically just keep doing that. So you can think of like a very naive approach is just for each blink, go through your array of stones, which are really just numbers, and do one of these things, right? It's not really that hard. The problem kind of gives you a hint, though, that leads you to memoization. At least it led me to memoization. What it says is, it says after you blink 6 times, there's 22 stones. And after you blink 25 times, there's 55,000 stones, right? There's a huge number of stones. That seems to suggest that the problem expands exponentially. And why might that be the case is there's probably a high correlation of numbers splitting, right? So if it's an even number, it splits. It seems to suggest that you get this split regularly. So, doing it 25 times is going to mean it's going to split a whole bunch. And you can probably do it 25 times just with the naive approach. But because you can see this expansion, your mind should immediately go, and we'll just talk about part 2 right now, to what if it's more than 25? What if it's a much larger number? And you can see that's what part 2 asks you, is it says, well, okay, so you've blinked 25 times. Can you blink 75 times? And you can see how much substantially bigger the problem is, right? So for the problem set, we go from 186 to this giant number that's way huge, right? And so again, with a naive approach where you're basically just looping through all the arrays and splitting them as you need to, or doing the multiplication as you need to, you could probably do that 25 times because you only end up with like 200,000. But imagine this many stones on your disk space, right? On your system in memory, that many integers, plus you are iterating over them one at a time to like increment them, right? Maybe the 74th time you only have half this number. That's still a huge impossibility, right? It's million, billion, so like 221 trillion. That should be something like when you see it like exponentially growing like that, you should say to yourself, oh, surely there's going to be a trick. And you could probably have inferred that from part one, right? Is where you say, okay, if you blink, once you get 3, you blink 6 times, you get like 22, and then you blink 25 times, and now you've got 55,000. That exponential growth pattern should lead you to think, oh, there's got to be a better way to do this. And so that's what immediately came to my mind was, oh, is there some kind of memoization or some kind of short circuit that I can do to make this easier? And so that's the approach that I took, was memoization. I imagine I actually haven't looked. I did look briefly at some of the memes, but we can look at the recap after. I imagine a lot of people solved it with memoization, unless there's some way for you to figure out some algorithm that says, oh, I can do math and say after n times you get this many stones. There's probably not a great way to solve it other than to say, oh, I'm going to memoize it. So I imagine the solution is memoization. But that leads to the question is like, what is memoization? So I have previous videos on memoization, I think, and dynamic programming in general. If you'd like me to go over those again, I definitely can. But, maybe we can just look it up. The idea of memoization is okay, let's look at the Wikipedia entry. The general idea is if you have this like recursive call tree where you're calling things over and over again, anytime where your call would repeat, you can cache that, and then the next time you call it, there's no need for you to repeat, right? No need for you to repeat all that stuff, all that processing that you did, right? Oh, hold on. No, I don't want to shut down. I don't know what happened here. Sorry. I'm going to try and go to a whiteboard because I think it might be helpful to just draw it really quick. This is a risky. I don't know if I've ever made a whiteboard here. Okay. We just want a blank one. So the idea here is, imagine you have, oh no, I had problems with this before, didn't I? Imagine you have like a tree like this. I probably should have tested this stuff out beforehand, huh? Okay, that seems to have fixed it. And you're traversing this tree, and this could be your functions call, your recursive ones, right? So this is, the number 5 or 50, and you blink 25 times, right? And then this is the number 5, and you blink 24 times. And then this is the number 0, and you blink 24 times. It doesn't really matter what the numbers are, but say down here, this one is, 0, 21. And so you actually go do the work, and you go down this tree and you solve it. So now you know what 0, 21 is. And so you know that the answer to 0, the number 0 that's blinked 21 times leads you to, some specific array right here, right? When you go down this tree and you see another 0, 21, you don't have to do all these calculations again, right? There's no need to do all this additional work. You can just say, oh, I've already seen 0, 21 before. I know what it looks like. So I can just return that equivalent thing. And that's what memoization is. It's just a technique where you it's essentially caching, where you say, I already know what it looks like, and I already know the answer to a question that I've asked before, and so I don't need to ask it again. And a very typical solution that they show you is the factorial problem. This way, where you calculate a factorial recursively, this if you do this very large, it can take quite a while. Most notably because you're doing the factorial twice, right? You're calling it multiple times. So as opposed to doing it multiple times, you can add it to a lookup table, right? Or this memoization table. And then anytime you can just say, oh, if I've seen this in the lookup table before, I can just return that value. I don't have to calculate it again. And it tends to save you steps in important cases. And that's where this comes into place, right? When you see this huge jump, you can say, oh, can I memoize? Will that help you? So I want to just show you what that looks like in code. You can see my solution is actually relatively short for the day. It's only 60 lines of code. I just parse the input, right? So I get a list of the numbers, right? And then I just call this blink function, but I give it a memo hash map. And again, the hash map is just going to contain like this part right here. It's just going to be a hash map of the number and the number of blinks I have and how far and what that result was. Remember, I'm only doing the count. I only need to know how many stones. So I don't even have to track the array itself. I can just track the number. And so that's what that memo contains. And so what I do is I just go through each of the numbers and I call that blink function and sum them all up, right? So I say, oh, this number is going to produce, this many stones, and I just have to add those up together. You'll see for part 2, nothing changes except for now instead of 25, I use 75. So let's look at how the memoization helps you. You can see for each blink, I'm going to pass that hash map where I track those values, that memoizer, and then I'm going to give the number and how many remaining blinks I have. So I know if I'm at no remaining blinks, I can just return 1, meaning there's only 1 stone, and I'm not going to blink anymore, so there's no way for it to split into more than 1, so I can just return 1. But then the next check is going to be, have I seen this number before? So if I've seen the number and remaining before, that memoization, basically, I've done this work before, so I don't want to go do it again. I just return that result. And if that is the case, if that's not the case, I should say, what I need to do after that point is now I actually have to go do the work of figuring out what that number is, right? So this is just implementing the logic that they gave in the problem, right? If the number's 0, I set it to 1, and then I call blink for remaining -1, right? So if I'm at blink, if I have 25 blinks left, I now and the number was 0, I now call it on 1 and with 24 remaining. And then once I get that result, I insert it into my cache, my memoization, and then I can return that value. If the number is divisible by 2, or the number of digits is divisible by 2, then I just split it up. This is probably not the most efficient way to do that. I'm sure there's a more efficient way. But I just split it up, and then I call blink on both of those sides, right? I call blink on the left side and the right-hand side with the, remaining -1. I get that result, and I save it to the memo, and then I can return the result overall. Otherwise, I multiply the number by 24, and then I insert that into my memo and I return the result. So you can see here there's a pattern where we say, oh, and I could probably clean this up more now that I think about it using like a match statement. Maybe we'll try and do that and see if it works really quick. But you can see like the idea is the way that memoization helps you is if you've seen it before, just return that value. Otherwise, everywhere else where you do a calculation, you save your results once you've done the calculation. So that at some point when I'm doing this recursive call, I'm going to get some number and remaining blinks that I've seen before, and it's going to allow me to skip it. And I could probably set it up to show you how absurd it is and in how it changes the processing time. In fact, it won't change at all. But like, just again, just to highlight it, that is the problem, right? Is like if you can say to yourself, oh, this problem scales exponentially, so I need to find some efficient way to solve it, and it's a candidate for memoization, that's how you get to solving today's problem, at least in my mind. The rules are simple enough that you could do it in a dynamic programming type way. And whenever you can do something recursive with these, with very static values, memoization is a key candidate. And so that's just something to look out for. Again, I've talked about it multiple times, so I won't get too much more into it. But let's just try, we can copy this and so we have our regular blink function, but maybe we call this blink no memo, and we will delete the memoization parts of it just to show you how bad it is. Oh, I missed one there. I need to rename all these to blink no memo as well. Okay, is that right? Okay, so we will run. You can see the first one only took 18 milliseconds. Oh, I guess I could do. I just do it like this. We'll do P2. No memo. And I can promise you this is never. It actually. Oh. No memo. I'm like, wait, why does that return so fast? And it's because I'm using. So why did that first one return so fast? I've already filled up the memoizer with the blink results, and so it knows immediately the blink results, and so you can see it returns in like a nanosecond or whatever, because it knows immediately what the answer is. Okay, we'll do it again. So there you go, and you can see it's not returning. I actually don't know how long this would take. It'd probably take years, or maybe until like the heat death of the universe to finish, because again, you're doing 221 trillion. Eventually, you're going to get to 221 trillion rocks, but to get there, you have to do like so many calculations to get there, right? So you can see it's just running forever. And this is really, I think, a very good showcase of why memoization helps. What you often find when you're doing recursion, I shouldn't say often, but many times when you're doing recursion, one thing you will realize is you're doing a lot of the work over and over again during your calculations, right? And so it might be useful for you to memoize it and to say, oh, well, I can speed up this algorithm like almost infinitely if I just memoize the results. And so that's just something to keep in mind as you're doing processing. And I've actually done this in like real world work stuff where I have some function and I say, oh, I can store the results of this function call and then just return it again if I get the same request. So this is something that I've actually found is applicable all over the place. Sometimes some of the problems you're like, okay, well, this is a fun problem to solve and it expanded my mind, but when will I ever use this at work, right? I think memoization is a very good candidate. They're called different things in different languages, by the way. Like I think in Python that they actually have like a you can create like an attribute of your function or whatever it's called, where you just say cat. You say like cache this thing, and then it caches it for you. We've been talking all this time, and it still hasn't returned. Right? It's just never going to return. So, we don't have to keep doing this if we don't want to. But hopefully, it gives you an idea of like how powerful memoization can be, and it is a common technique in advent of code. I've also seen it in like leak code problems. So if you're really into problem solving, or you're prepping for interviews, memoization is not. It's definitely a word that you can say or a tool you can use that might get you some brownie points or might help you solve the problem, right? Even if, like, say you're in an interview and they ask you a question and the solution is recursive, one of the questions you might ask during the interview is like, oh, would this be a good candidate for memoization? And you can work through that, right? How often am I calling the same thing over and over again with the same values? And if you're doing that a lot, then memoization might be a good technique for that. Um, okay, so what else? Oh, I thought we might be able to clean this up a little bit with a match. Uh, is there a way to do this in a match? The problem is like this is different from this. So like the question is like, what are you matching on? It would be something like this may not look good, but you could do like match number equals 0 s dot len divide nope, I will get the right number. Ampersand 2 equals 0. Like that doesn't look very good. But we can say let result equal, and then we can change all these. And then we'll be able to put all these down here. That's what I'm thinking. You'll have to tell me what you think. Which way do you like better? We don't need this one anymore. Semicolon. So like that, does that give me the right answer? Yeah. So I don't know. Does that look better? You could also just do the let result equals if, and then return these values. Maybe that it looks even better. If number equals 0. What was that? Else if s dot len modulo 2 equals 0. Do this. else do that. Like that. Maybe that looks better. Like, because an if is an expression as well, you can do this. I think that still gets you the same results too. We can double check. Okay, so that is a third way. This third way probably seems the best to me. Anyway, you tell me what you think. But just to recap, the day is definitely about, can you memoize, right? So that's kind of where I went with it. We can go look at other people's solutions. Uh, okay, the blinking guy meme. Yeah. Day 11 thought it was clever not taking the bait for part 1. Realized early in part 1 that the order of the stones doesn't matter. Part 2 will run out of memory faster. Yeah, so this is the thing, is like, again, I don't think where the stone is matters, because if you think about what's happening is that the stone itself is just splitting, and the order doesn't matter because you're just counting how many stones you have. So putting it on the end definitely makes it faster. So I almost wonder if that their order is preserved, if that's like a trick to make you think, oh, if I'm going to be doing, at least in part 1, if I'm going to be doing um like array manipulation, I'm actually going to have a list of rocks, and I'm going to add, so I need to split this rock. You now have to like insert it into that position, which may make you think, instead of using like a vector, you should use a linked list. That would probably be the better solution. Uh, and it would work for part 1, right? What is the size of part 1? So you can definitely fit this many integers into memory, right? That's not an issue. I'm highly suspect that, you'd ever be able to do this one, right? So you could do that for part 1, and then you in part 2 you'd say, "Oh, I got to do it 75 times. How do I do that?" That's an interesting solution though for part 1. If you happen to do yours in a linked list, I'd love to see it, because I think that's the way I would do it. Is if you're doing these inserting and you're worried about the order, that's kind of important. But you do, if you read the program and think about how you're adding the stones, it doesn't actually matter, right? What is this? Very cool and oddly. I don't want to click here because it's going to use my camera, right? I think that'll kill my stream or whatever, my recording. I have no idea. Oh, he did it in Scratch. That's very cool. Of course you failed me. Yeah, you can't. I mean, again, you can do it for part 1. You can very literally have a list of rocks and expand those rocks, and that should work fine for part 1. I don't know how fast it is, but it should work. Every sequence converges to 3,948 points. There are where all sequences eventually converge to cycles of lengths blah and blah, or at least finite attractor set of numbers. I actually have no idea what this is. Is this if you go past like 75? Okay, 75 factorial. Yeah, maybe what it's saying is like if you get high enough, you can, like if you do it past 75 blinks and you do it a whole bunch of blinks, you eventually, each one converges to some known value. I'll just change the number of part 2 easy enough. Me waiting approximately 171 years. Yeah, it's going to take a long time, right? No matter how the stone, their order is preserved. Whoa, this is okay. Yeah. Yeah, this is a key thing. Like if you, I wonder. It would be interesting to ask Eric what he means by this. Is like, was this intentionally a trick? And are there sometimes tricks in these things? Because it doesn't. Usually, when it's bolded, that's it. The like, it's meant to be like, hey, you need to pay attention. It's not just Easter. Some of these have Easter eggs, by the way. Have you guys found Easter eggs before? Hovering over things will sometimes give you an Easter egg. But the bolded ones are generally meant to be like, hey, don't, this is important. Don't forget this. Okay, let's look at a couple more. Posting here. I'm in danger. Oh, the input size is relatively small. And so you may think it's not a big deal, right? Is like, my input size only has a few numbers in it. So you may think, oh, that's not a big deal. But this is the thing is like with exponentials, right? I'm sure you've all seen that thing of like, would you rather have $1 million or a penny doubled every day for a month or something like that? I don't remember what it is. When you're growing exponentially, it gets really big fast. So, and this is just one of those days that it's good to figure that out, right? So if you didn't, that's okay. There's no harm in not figuring it out. We can go look at solutions and see if people solved it another way. But almost always is the case is when you run, and I've done this before. I happen to realize, oh, this is going to be a memoization problem, and got there with part one. Um, but I've had it before where I haven't realized, and so I've ran part two, and it's just taking forever. And then I'm like, okay, how do I optimize? And just keep that in your back pocket. One of the ways that you optimize is memoization. So if your function is already recursive, think about that. Haskell, golf version of my earlier effort. Not used Haskell for a long time, but I love the syntax. Okay, it already says it's using memoize. R equals memoize to where? So 0 becomes 1. Anything and 1 calls it again with 1. The even lengths, you call it again over the two sides. Otherwise, you do it this way. Okay. I mean, I tried Haskell last year. Take drop. So I understand most of this, but it really, it's like mine is just doing it in Haskell, or everyone's, right? I'm sure everyone got the same answer. It's not like I own the memoization one. Took a while to come up with a solution to this one. I was finally forced to come up with a solution faster than brute force every day up until now, even though I should say one of my early thoughts was, is the solution to this to use something like Rayon or Tokyo? Tokyo would be interesting. The reason I was thinking Tokyo was like, can I, for each of the blinks and for each of the values in the blink, can I do a spawn a thread? But they're like Tokyo tasks, I think is what they call them, right? Can I spawn a Tokyo task? And so I can do a bunch of them in parallel. I didn't end up solving it that way because I was like, wait, whoa. Surely they don't want me to do a bunch of like parallel programming to solve it. First time trying to solve in Go. Okay, so it may be crappy Go code, or at least new split. I mean, clearly it's using memo. So if there's no blinks left, return 1. If the memo's in there, return it. Otherwise, do the things and then return the results of the memo. Okay, this one looks a lot like what mine was. Is even length. Okay, this guy's using the math. Again, I just turned it into a string, and then I used the split. I split the two of them, right? You can use math to get the first and last halves, which is what he did here, right? So this is the mathy way to do it. I think we saw that in a previous day. There's like a kind of an easy mathy way to get n digits. So in this case, we're getting half of them, but you could potentially get any number of digits from the thing. So Okay, very cool solution in Go. And I think this code looks pretty good. I mean, this if I was doing a review at work, this would look like, you know, the average developer's Go thing. So if he's first time trying to solve in Go, that looks pretty good. Elixir, Kotlin. Should we try and find one in Rust? Did I just miss this one? Split, wipe, space, parse, collect, unwrap. Yeah, that's perfect. Oh, you can see in mine. I didn't really highlight this at all, but like I do really like this split map collect over to the result, and then if I have my main function just return a result, I can I can do the question mark operator here, and so this value is a vec of view size, not a result of a vec of view size. But this works just as fine too. I don't know what I have against unwrap. It's just when I think about doing real work, like the only case you'd want to use unwrap is like with mutexes and things like that, right? Where if like it failed, the unwrap of a mutex failed, something's seriously wrong, and so you should blow up the program. Okay, let's go back to the code. First star. Get the input. Next stones for stones and stones. Okay, so for the first time, he's actually, for part one, he is actually, or they are actually uh, creating a new set of stones and shoving them in there, right? So literally, he's going stone by stone and saying, what should be in here and what should I push in there, right? So it's like if the stone is 0, push a 1 and continue. Otherwise, split it, or if it's divisible, if the length is divisible by 2, split it and call push on the 2 stones. Otherwise, just push the stone multiplied by 2024 and then do that 25 times. So this is like the what I was talking about before. You could do a literal approach of adding stones. The way he gets a so he's not notice he's not doing inserts. He's just creating a new vector and adding those values back in. Potentially, I don't know. It would be interesting to know the difficulty of inserting a value in a vector because it usually involves a move as opposed to just like creating a new one. Anyway, what does he do for the second? Uh, how does that even work? Part 2 was an adventure. I initially wanted to do a full memoization, but I struggled for way too long on how to properly propagate already solved node zones, and when I managed coding something that looked like what I intended to do, it was even slower than brute force. Then I gave up and just counted how many stones I had for each IDs and on each turn, and that was both faster code and took less time. Like it does, if I'm reading it right, it looks like it's memoization. Basically, he like for each stone, he does the work and then saves that up here. But I don't see him doing memoization. Doesn't look like it. I kind of want to run this code. By the way, the thing that came to my mind is you don't have to solve this recursively. You could have a stack like what we had done in the previous day, and you just like keep pushing your to do work on the stack. And then you have a hash map of said, oh, if I've seen this item, do I put it on the stack? Essentially, you're taking the actual program stack and turning it into an actual like a data structure stack, and you can solve the problem the same way that way, right? Which I thought is what he was kind of doing right here. I'm still failing to see. So you have a list of stones with a value of 1, and you increment 4 blink and blinked stones. 1, 2. There must be some counting mechanism. I don't understand how storing it as a hash map. I must be missing how to solve it that way. Maybe his intelligence is beyond me. I kind of want to run his code just so I can see how it works. Where are we at? Okay, yeah, we got time. We can. I don't want to like bore everyone. Get input into iter. What does his get input function do? Okay, so we can just add this right here. Uh, I tried to remember a key binding and it failed me. Was I mean, that's really fast. What am I missing about what he's doing? Why am I not understanding this? You have a hash map that contains the value of each box and value of each stone and a 1. You loop, so you're going to do 75 blinks. You create another hash map for the next set of stones. Go through all of your existing stones. So you're going through all of your existing stones. Oh. If you've seen that stone before, you just count it up. Okay, I see what's happening. Okay. So you have a hash map of all like the numbers you've seen before, and then you just track how many times you've seen that number. Um Yeah, so why does that help you? Probably because the unique set of stones is smaller than the 221 trillion. Like there's maybe only, you only have 10 inputs, and maybe those 10 inputs only explode to um even a million unique numbers is small enough that you can do this counting. Okay, so now I understand what's happening. Yeah, that's a really cool solution. Is you say, "Oh, well, I just track how many times I've seen a stone of the given number." Um and then I don't have to recurse through those. And you just do that. What's happening is you just are expanding that number, right? So each time you go through that key set. If you've seen, a number before, you figure out what that number turns into and you count that many times. That's a really cool solution. Like the way it's hard, I probably can't draw it out to do it justice, but the way to think about it is, if you're using like the array method, if you have the number 0 in there 5 times, there's no sense in calling the function on the number 0 5 times. You just call it once and take those results and put it back in the map. But you have to do it 5 times, so you add that many times that you did it into it. So that's really cool. That's a cool way to do it. Where is that guy? I should give it a thumbs up. Counted how many stones I had for each ID on each turn, and that was both faster to code and took less time to compute. Yep. Very cool. This may actually be faster than memoization. I mean, it looks like it's faster on this last run. What did I do there? Like, my guess is, like, it looks like it's generally about a little bit faster. So maybe it's like some small amount faster, but not like an order of magnitude. But that's a really cool solution. Okay, let's find one more Rust. I'm happy how concise and I think readable this turned out to be. Helped a bit that I reached for a library for memoization instead of the manual hash map passing. Cached? How does that work? Cached provides. Okay, I think I've actually used this before now that I read it, but it didn't come to my mind when I was trying to solve it. It's like a memoization. I don't know if I've used this specific one, but you just give it, you just derive, or you just give it the cached tag, and then it kind of wraps this into, it does the work of the memoization for you. So that's a very cool solution. So readability, part 1, stones, part 2, stones, split wide pace, parse, contact, collect. Is using anyhow. I don't think I've ever. I don't know if I've used anyhow in these problems, but anyhow is a great way to like uh, kind of handle errors for you. Let it handle errors. Excuse me, for you. Sometimes, oh, I got the hiccups. Hold on. Count steps recursive. If it's 0, return 1. Else, step into iter map sum. Okay, here's where you do the logic of doing the work and returning the values. Yeah, I think it's pretty good. I like it. I think you could do it in fewer functions and it'd still be reasonable. But uh, everyone. I'm a big fan of functional programming, so you try and solve this in a functional way, and that leads you to maybe want to do this inline and this one cached. Oh, this is the one that's cached. That's what. Sorry, I misspoke earlier. This is the one that's cached. This one's marked inline. I don't know how much inlining helps you there, but very cool. Should we try using this cached thing? See how much it speeds ours up. What? Does your Google ever respond to you? You don't want it to? Running a cargo, add cached. And then I just add this. I do cached like this. Oh, if I'm doing it this way, I can actually go like this now because I don't need the result. Get rid of this. I don't need the memo. One of the nice things about using the memo for both the parts, if you reuse it, is it's already solved for 25 and below right here. So you only have to do the larger one. Admittedly, it does expand quite a bit, but yeah, I mean, that is the same answer, and it actually is faster. I guess I'm not using a hash map anymore. Okay, that's cool. I had forgotten. I don't know if I've used this specific one, but I've used one like this before, and it feels like it's consistently faster by a little bit. So like on the order of like 3 milliseconds or whatever. So very cool. I did not know about this. That's very awesome. One more. Multi-threaded recursive memoized version. The results is extremely fast. This might be the one I've used before. I think it's this one. This is probably the one that I've used before. I actually don't know what's faster. Which one's faster or newer? Crates.io. Memoize. It sounds this one seems like really bigger. So this is the one I think I've actually used before, but it sounds like the cached one is the new cool one. So maybe stick with that one. Let's go back to a solution. Blinkstone. I mean, once you know that you memoize, yeah, it's super fast, right? You just call blink on it for each of the numbers. Maybe this one's really fast because you can pick your hasher. I don't know which one this prefers. I don't want to read the document. I don't want to just like stand and read the documentation as you're watching me. I don't know. Maybe you like to watch people read. People like to watch people do lots of things, but it looks like potentially you might be able to get this one to do the same thing. Anyway, that's cool. I had forgotten that you can actually do that. So now you don't have to implement your own cache or memoization. You can do that yourself. And this is actually like this right here looks a lot like what it would look like in Python. I think it's like there's like a func tools or something like that where you say cache it and then it's cached. So that is very awesome. Very cool. One more and then we'll be done. Rust that compiles to WASM used in a solver on my website. Bonus link at the top of the code to a blog post about these. Okay, it looks like he's using the other solution that I was talking about, where you just need to track the number of stones, and then you just go through the stones and keep incrementing those numbers. So you don't have to. The idea being there's some unique set of there's a substantially smaller subset of stone stone numbers to total stones. Okay, yeah. I think this is a good catch. It I mean it's sort of I said it myself. The idea is like if you understand the way the problem goes, uh it will lead you to believe, oh, this doesn't make sense. The order is not preserved. The real thing is like saying to yourself, "Oh, how do I figure out how to build these? If I'm only counting the number of stones, does the order really matter?" And it would only matter if it was like if a one is next to a two. Now order does very much matter, right? And that would make the problem substantially harder. You'd have to find some other way to do it. Um, Parsing helper. Is this a link to the Zoolander thing? What is this?
Without much further
School
ado,
for ants?
I give you the dare.
Okay, I probably gonna get DMCA'd for that. I probably shouldn't click the link. Let's see. He doesn't really describe how to. I mean, he kind of does right here, but like the intuition behind this, I would be interested in knowing what is your intuition behind this. And I think the key to it is the number of stones is large, but the number of unique stones is small. And so using this hash set is important, or is a valid way to solve it. Anyway, it is a very cool solution. So there you go. I think that's enough reviewing codes and memes for the day. And shout out to Zoolander, I guess. Hopefully I don't get DMCA'd. Anyway, I liked the day. I thought it was a fun day. Hopefully you had fun doing it too. Always, as always, love to see your solutions, regardless of the language, especially if you did something unique or you tried something different. Or if you just did it in Rust, I love to see it because, like this, I had forgotten about these type of things, and this would help a lot, right? Imagine, especially if you're saying to yourself, "Oh, I want to be competitive in the speed part of solving it." Knowing about this library is potentially really important, right? You probably don't use Rust. You go to like Python or JavaScript if you want to be like competitive. But if you're like, "Oh, I want to be competitive in Rust," knowing these like tricks right here are super helpful. Especially like saying, "Oh, I know," like we've used some of the graphing libraries before where you say, "Oh, I don't have to implement DFS again. I can just give an existing package my neighbors function and my what to do function, like my what to do at each node function type thing." Uh anyway, so there you go. Really fun day. Again, if you're not familiar with the memoization, look it up. It's worth looking up. That's why these problems are fun to solve, is there's definitely going to be days that I won't know. And so I will just start Googling or looking through like papers that have algorithms to be like, "Oh, what algorithm solves this problem?" to see if there's not some way to do it, right? Ooh, I don't have time today, but one day it might be interesting to ask Claude again or some kind of GPT. I know I did do that in previous days. That might be fun to ask again just to see what it comes up with. But there you go. I had a lot of fun with it. Hopefully you had fun with it too. Leave some comments down below. How would you do things differently? How did you do things differently? And we'll see you for tomorrow.